Hello, good afternoon, everybody, and thank you for joining this new session or new series of webinar for 2026. And today we have, I need to make an announcement first with the upcoming of the Panglass meeting next July in Stuttgart. And there will be a dedicated session for machine learning, for land modeling there as well. So please register yourself. I've put the link in the chat. And for our today speaker, Dr. Manmeet Singh, who is an assistant professor at the Western Kentucky University. His expertise is very well fitted to the ML4LM webinar series, as his interdisciplinary research lies at the intersection of climate science, artificial intelligence, and Earth system modeling. And before joining the Western Kentucky University, Dr. Singh was distinguished postdoctoral fellow at the University of Texas, where he worked in the AI augmented weather and climate prediction system to improve the extreme weather forecast and health impact and disaster. He also served as a scientist in the Indian Institute of Tropical Meteorology, contributing to national climate modeling effort and leading several projects on the aerosol monsoon dynamics and climate data downscaling. Dr. Singh holds also a PhD in climate study from the Indian Institute of Technology, and he was involved in several international collaboration, such as the Paris Olympic 2024 research demonstration project and the Earth virtualization engine. And today he will tell us about the EarthMind S2S, which is a coupled ocean, atmosphere, land global AI model for subseasonal to seasonal forecast. And the key element of the EarthMind S2S is the AI land that represent the land surface state and memory processes like soil moisture, snow, groundwater, and vegetation, and their related energy and water flux. So this up to you, Dr. Manmeet.
Thank you, Dr. Sohail, and thank you so much for giving me this opportunity uh, to talk about this model and the work that is really like close to my heart. So this is Earth's Mind S2S as we call it, and I'll be talking a lot more on the Earth Mind AI land model, the land model in this. But first, I would like to take the audience through the developments in the AI weather prediction world, because I come from a time when we were developing the IATM Earth System model, which participated for the first time in IPCC, and I've been like a developer of climate models, uh, from like doing everything in Fortran to things have now completely changed. So I think this figure on the right, from Peter Bohr's 2015 paper, The Quiet Revolution of Numerical Weather Prediction. It clearly shows the progress numerical weather prediction made, and land surface has been a very important key factor in this progress. I have been very closely involved with the team that has developed NoMP model, and have had exposure with CLM, the other land models as well, like Jules and others. Uh, with different models having their different capabilities. So as we can see that the northern hemispheric and southern hemispheric at forecast skill at different lead times, it kept on increasing. but then hybrid models was what I was doing at that time. But now we have come to the stage where we are now dealing with full end-to-end AI based weather models. So yeah, I think this paper is I think would be considered very classical even now and in the coming future. Uh, they first for the first time
Sorry,
discussed.
Manmeet,
Yeah, yeah.
may I interrupt you? Because I see that Ed and Maria has their hand raising. Maybe there is a technical issue or something.
Okay.
Uh,
Um, is it okay? I mean, am I audible? And
so if there is any issue, please write it down in the chat or in the Q&A, please. Okay,
okay, so okay. Uh,
okay, please.
Yeah, thank you. So this paper I think would go down as one of those classical papers where the authors they tried something really simple and in simple I mean like just I think two variables: geopotential height at 500, temperature at 850, uh, time t as input, t plus 1 as a target as an autoregressive model. And since this is a unit which has convolutions, and this was published in 2019, and that decade, like the past decade, was the one where we had explosion of convolution neural network based computer vision models. So they tried that, and what they were able to reach was just order of magnitude of skill which was similar to CFSV2, which was climate forecast system version 2. And these numerical weather prediction models or the earth system models are coupled models having different components. It has taken so much time and effort and resources, maybe the last 4 decades. And then a simple model like this, uh, reaching the skill of a really state of the art model, which has like the physics based model was I think was a news to the community. And then the next work that I really liked, and I'll show some of the earlier work that I was also doing. So they try to understand uh, in this 2020 paper how to basically further improve the skill of the DLWP, or the deep learning for weather prediction model. And then they found out that basically in the earlier version they were treating the earth as a like earth is a sphere, so they were treating it as an image. But then that would be having its problems in a way that it would introduce spherical distortion. uh, for example, Russia would look bigger, Africa smaller if we just do the projection in Mercator or Latlon projection. So they use this grid, which is the DL cube sphere, which has been used like extensively in the field of Earth system modeling and or numerical weather prediction. And now you basically have six faces along the tropics, two along the poles. Now each of these faces can be considered as an image, approximately as an image, and the spherical distortion error, it actually went away. And so they at the same resolution they were able to beat at different forecast hours. They were able to beat the skill of IFS, and this was with four variables. They were training a UNet model, and then at the same time, like and I was trying to develop hybrid models. So what we actually did was, instead of having an autoregressive framework, because precipitation forecasting, I come from Indian Institute of Tropical Meteorology, where the goal of, like, it's a 400 scientist institute. The goal is basically to improve monsoons, and monsoon is something that drives the economy and everything, livelihood of about more than 2 billion people who live in South Asia. And so what we did was, we were trying to see whether, if we input, like if we have a unit in this way, and try to improve or try to develop the relationships of precipitation. Can we actually do that? So taking different fields as input, like total cloud cover, surface air temperature. And that was a time when weather bench actually came out. Weather bench was is basically just aggregated era 5 data at different resolution, but they made it in a way that it could be ingested into the machine learning models really easily. But also, I will talk more about land, like in a short time. Everything that was going on was atmospheric model. So all the hype, all the models, the explosion, so many models that we have seen, all everything in the atmospheric models. So this was, this was, for example, this was a median of day one precipitation ground truth, and then we checked the median of GFS, how linear regression looks like, how total cloud cover to precipitation and 2 meter temperature to precipitation model looks like. Things were looking pretty good, in fact, and I think, so this was basically, this was published in 2023, but the work was done sometime in 2021. And that's what we are seeing these days with these large models like GraphCast. Precipitation is really good, and precipitation has been a big problem in the models, the numerical weather prediction models, from a long time. A lot of efforts are like the end goal is being said to be improving precipitation. So we tried to see the skill over different regions. It was basically beating GFS at over different regions globally, the different metrics that we were seeing. And then what we did was, the next step was basically to try and see, can we make a product out of it. So we took the North American multi-model ensemble hindcast CFS V2 hindcast data. Now CFS V2 has got the land surface component. It's a coupled ocean atmosphere land, sea ice. There are all the components are there in the model. It is used for seasonal forecasting, and for other purposes, for short range forecasting in India, and as far as I know, like in US as well. So there was this hindcast available from CFS V2 1982 to 2010. This has been, this was called North American Multi-Model Ensemble. So I took basically day one, day two, and day three lead forecast of precipitation and temperature. Uh, Took that to a cube sphere space, and with a unit mapping. So this was like for temperature and precipitation, those are like 6 maps, and then those transformed into cube sphere, and then corresponding ground truth was era 5 precipitation. So but at the same time, for which like the it was like co-located in time, and then the training was like, this was like really large experiment, 1982 to 2000, the validation data from 2001 to 2002, and test data from 2003 to 2010. Now why I'm saying this is, this was huge because NMME has every 5 days, they would have a hindcast available, and every day whenever they will have it, they'll have for 00, 06, 1, 2, and 1, 8. So four initial conditions. They had the data. So this 2003 to 2010, all the 7 years, but then like so many sample hindcast runs. So we published this in 2022 in NeurIPS. What we actually saw was, so this is the operational short range forecast system. Now they have something better, which is called Bharat Forecast System. But this was from a previous paper, 2019, that they published. So we wanted to see how our hybrid physics AI model performs relative to the traditional physics-based model. And this is the iMerge climatology over India. Day one, day three, day five, and day eight. Day 8 for like climatologies, and then the bias at different lead times. So you can see that for like these are important regions for agriculture, and not just agriculture but rain-fed agriculture, where the agriculture is dependent on rainfall, and agriculture is what is still driving major economic it's a major economic driver in these regions. So even like this is the mean bias, upwards of 10 millimeters per day is like huge. What we actually saw in the hybrid model was that this bias, and this is from the test data for different seasons: June, July, August, September, October, November, December, January, February, March, April, May. It came down to within -1 to 1 millimeters per day. Now, this was the mean. But then when we started looking at the individual cases, so for example, this was one big event in 2005, which is the Mumbai heavy rain event, at different lead 1, lead 2, and lead 3 forecast. Uh, so the CFS V2, it had a lot of positive bias over the waters, Arabian Sea and Bay of Bengal, and also over the land, which was being corrected by the hybrid physics AI model. And then similar examples for other case studies like Cyclone Nargis over Myanmar, Hurricane Katrina in 2005, Hurricane Ivan in 2004, China floods in 2010, Central Europe floods 2010. And then when we saw the metrics, so the numbers were really encouraging, like about 10x improvement quantitatively for the like average or the climatology, and then for each of like the events, it was like even more. And then like fast forward, we have now seen explosion of these AI weather models. So I was talking about the DLWPCS type of model, which took into account just four variables. But now Pangu weather, this was I think published sometime in 2023, mid of 2023, that took all the variables of atmosphere, almost all, like they might have skipped some of the vertical levels as input, and then trained in an autoregressive manner with a 3D specific transformer. But they also considered the sphericity of the earth, as in they took the cube sphere, they took it in the cube sphere. And what this saw is that, so the blue one is the ECMWF HRS forecast, and the black is the ground truth, and the red was the Pangu weather forecast. I think this completely and this was an end-to-end AI model. uh, I think this completely changed the way the entire field of meteorology actually looks today. And then there were a lot of different other models like GraphCast from Google DeepMind, wherein they also would consider the sphericity of Earth, but consider the sphericity of Earth in terms of, you assume this Earth as an icosahedron. Now, an icosahedron has got five triangles on the top, five triangles at the bottom, and then if you can see at different levels of that icosahedron at m equal to 6, that approximately looks like a sphere. And then each of these nodes can be considered nodes of a graph, and then you train in an autoregressive way. But this is also an atmospheric model. This paper came out I think end of 2023, and it showed a lot of improvements, and really nice extensive comparison with the ECMWF IFS HRS. Other model that came out was and why I'm talking about all these models is because the architecture is really important, whether you are treating the earth sphere as a cube sphere, as a graph, as like in forecastnet they considered as spherical harmonics, and these are the building blocks that would be required to build a land model, an atmosphere model, an ocean model. So I'll be talking about the land model that I have built, but I wanted to touch upon the flavors of the different architecture. So in ForecastNet, they consider the data, the latitude, longitude data first as, so in the ForecastNet version 1, they called it AFNO, which was Adaptive Fourier Neural Operators. Now that was based on the 2D FFT, but now what they have transformed this in ForecastNet version 2 is SFNO, which is Spherical Fourier Neural Operators. They also have recently version 3 model, which shows even seasonal skills. So in this, they first take the data to a spherical harmonic space and then train in an autoregressive manner, the similar way the previous models were trained, and really nice forecast skill with forecast net model. And then the Fushi model. So Fushi has been a model which also use t and t minus one times and t plus one as target, cube sphere embedding, and a U transformer. So eventually, it is all boiling down into you basically transform the data in some form that we respect the sphericity of Earth, and then we do an autoregressive mapping in which basically, so the U transformer in this case, or the UNet, they take care of the spatial patterns or the spatial relationships, and then we model the temporal relationships, give time t as input, t plus 1 as a target, or additionally also take t minus 1. There are some papers which also take some other previous time steps. So we are basically trying to capture the spatio-temporal variability of the Earth system. And then there has been this model called Swin RDM, in which they also in addition to cube embedding, and the image to image model that they use is called Swin Transformer. They also use a diffusion model to basically generate high resolution forecasts. Neural GCM, they have come out with a really nice update. I think that's just this week. So this is one of those models. It's a closed model. It's not open source, where they have just replaced the entire physics of the model with a deep neural network. And this is one model which also consists. They say the land surface embeddings, the CIs, those things are also there in neural GCM, but the code is not open source. So this is like just with the Google team. And then there has been this foundation model Aurora, which was built by Microsoft. They used all sorts of input data to this, the ERA 5, CMIP 6, GFS, uh, and that's the reason they call it foundation model. In addition to what the previous works are doing, they also take into account the chemistry components. So they have the air quality forecast as well in the Aurora model, and everything. All these models, again, I would say that we are talking about are all models for atmosphere. And then there are efforts going on for high resolution. I'll not go into details on that. And Weatherbench 2 is a really nice benchmark. I think we need a benchmark for maybe coupled models or AI based land surface models as well. Uh, Weatherbench 2 is a really nice effort that actually showed that GraphCast operational actually at different lead times, it is able to it surpasses the skill of ECMWF-IFS, which is like uh, considering the time of development of these models and the time of since the physics based numerical weather prediction models have come, it is actually tremendous. Now I'll come to the model that I have trained, but before that, I've used basically this grid, which is called heel picks. Now, heel picks is another way how you would represent latitude longitude grid. Uh, so we talked about cube sphere, spherical harmonics, graph. Heel picks is another way. This before this work, I think this they talk about this grid being used a lot in astrophysics or astronomy, and when they actually used the Helpix grid, it basically consists of 12 faces. Earth, like the sphere is consists of 12 faces, and what they showed was that when they ran the model, and this is again they ran atmosphere only model. When they ran for long period or like the year long simulations, so heel picks and spherical harmonics were the only two meshes that were actually stable and that did not blow up. Graphcast, Pengu weather, they and then delta t, the temporal mapping also matters. But they, I think they tested whatever was available. So these are the two really nice. And what I have observed is that hill picks is a really stable and a really nice grid to work with. And then this work, so coupled ocean atmosphere dynamics in machine learning assisted model, or what they call as OLA, or ocean linked atmosphere model. This was the first coupled ocean atmosphere AI based model where they actually trained an ocean SFNO in addition to an atmosphere SFNO. And in the ocean SFNO, they are taking the outputs of the GFDL sphere model, which is also again a physics-based model. And then here they are taking a delta T of 48 hours and then doing that building offline models. So the ocean model, when you train, it will be having atmospheric forcings. Atmospheric model will have ocean forcings, like as in the ground truth. But then when we run these models, when we run the rollout forecast, at that time, the ocean will take the forcings, the some part of the atmospheric data, which will be the atmospheric forcings. Atmosphere will take ocean. So, for example, sea surface temperature or sea surface salinity, and the coupling basically takes place every 48 hours. So, this is the philosophy, I would say, like from Hillpix, and the way that this coupled ocean atmosphere model works. Uh, I actually started working on developing an AI land model because eventually, when like I will maybe talk for 2 more minutes about S2S. So there recently now there has been a lot of developments in short range models, uh, 15-day forecasts, like these so many models, GraphCast, and these days now we also have the weather next two series of models from Google. Skill is looking really good at up to 2 weeks, but then the next frontier is basically S2S, or like 45 days lead time, or like 6 weeks to one season in ahead of time. And all the so there are many AI S2S models now. I would say I think AI, the ECMWF is running a competition called AI Quest. I have a slide on that. I think there were about 28 models. Some of them are closed, some of them are open. So some models that are open are, one of them is Fushi S2S, and again they are just using atmosphere only data. So ERA 5 atmosphere is the data that they're using. Some changes in the architecture as compared to the AI atmosphere models, but and also these models take into account, they are like probabilistic, so they have ensembles. Then the other model is Fengwu W2S. They compared the results with Fushi S2S and with ECMWF. And then ECMWF published this AIFS CRPS. So all the blues, I think, are where they basically improve on the physics-based model. And the way they generate ensembles is also really novel in this work. So this is the AI quest and all the different models that are participating in this. A lot of them actually have now started taking into account land surface. My motivation was basically to develop a model which has the same philosophy as the physics based Earth system models, which are different components of land, atmosphere, ocean, and then they are coupled to each other. So that would basically come together to form what we are calling as EarthMind S2S. And the land component of EarthMind S2S is basically the EarthMind AI land model. And that's the background on this. So this is the architecture of the EarthMind S2S. EarthMind S2S architecture, in which this is the land model, that the training is complete now. We are able to generate offline, even S2S scale simulations from the land model. And this land model, and our atmosphere and ocean models are also hill picks. So they are basically trained on the era 5 data. The delta T in this case that we are considering is 24 hours for atmosphere, land, and ocean. And the Latlon mesh first is transformed to a hill picks mesh, and which basically goes to image unit. Now that is also something that we will be playing around a lot. We will be trying swing transformers or diffusion models or flow matching models or distillation models. There is a spectrum of models out there. And then the target is basically T plus 24 hours for in hill picks. So training is done in hill picks, and then there is a Latlon to hill picks and hill picks to Latlon transformation. And then when we have to roll out a forecast, so you start from some initial conditions, run atmosphere, land, ocean. Then the ocean model forcings go to the land, atmosphere go to the land, lands go to the atmosphere, ocean goes to the atmosphere. So every 24 hours, this coupling happens, and that's how the model keeps running on its own. There is a rollout forecast, and the model can actually run just like a physics-based model can run. You just need an initial conditions to start, and then you can roll out a forecast and run the model for a long time. So the land component of the AI, of the EarthMind S2S model, is the Hill Pix unit pipeline. In this we have the Era 5 land via Arco Era 5. Now one big challenge in this one was basically downloading a lot of data. So that is a big problem, and that is now solved by ZAR. So we don't download anything. We are directly training, like in real time, fetching the data from Google Cloud ZAR from Arco Era 5. First transforming the hourly data to daily aggregates, daily means, and then finding out the min max values. So min max normalization is done. And what is basically done is so 17 variables are taken in this, in the input, and 8 variables are taken for the target. So the 17 variables input that are taken are, so for example, for the land model, we'll have forcings from the atmosphere. So we'll have 2 meter temperature, total precipitation, 10 meter U component of wind, 10 meter V component of wind, surface solar radiation downwards, and these are the range of values. The evaporation, skin temperature, snowfall, mean sea level pressure, and then 4 vertical levels of soil moisture and soil temperature. So the variable soil moisture in ERA 5 reanalysis is called volumetric soil water layer 1, volumetric soil water layer 2, 3, 4, and soil temperature, it's soil temperature level 1, 2, 3, 4. So it's 17 channels, 17 variables input, and then this is a 3D unit. Why I'm saying 3D unit is because the Latlon gets transformed to, so the Latlon is basically 720 cross 1440, that is for 0.25 degree data. that gets transformed to 12 cross 64 cross 64. So 12 is the faces of the hill peaks, and then each face of the hill peaks has got a 64 cross 64 resolution. The loss is a mean squared error lost, Adam optimizer. So that's how we aggregate it at daily, and then make those supervised learning pairs in real time. We don't download any data. That's how the model is trained. And then the rollout forecast, for the rollout forecasting, you start with some initial condition and forcing, predict t plus 1, and then for that t plus 1 you take out the atmospheric fields, and then for the next day's model, you basically give the forecasted soil variables, but the actual forcing of the atmosphere. It's just like an offline model actually runs, and that's how we can predict the t plus 2 soil parameters or the land surface parameters. If this was eventually, when this runs as a full S2S model, in that case, the forecasted fields from the atmosphere model would be going into the land surface model. And then the model actually started converging. We started checking the rollout forecasts. So for volumetric soil water layer one, and then there were different design choices that we had to make. I think I did not talk about in that architecture slide. One was basically over the ocean. We uh, we would have nans in the land model. So how to deal with that? So the original ocean linked atmosphere, the OLA paper, what they actually did was they took the linear interpolation from coast to coast when they were building the ocean model. So in this case, what I have basically done is done bilinear interpolation, like because we need some values over the ocean pixels as well at the time of training, but after inference those values are basically masked out. So the prediction and the ground truth, you can see up to 9 day rollout forecasts were basically run for it. This is the surface soil moisture. This is layer 4 soil moisture. Overall, like broadly visually, it is picking up the spatial pattern for the soil moisture and also for the soil temperature. And then we thought, okay, let's try to run this in for a real use, for a real example or a real case study. So for example, this was 2019 wetland event, Midwest and Mississippi River basin flooding, and causing a lot of damage. So the way we have run this rollout forecast is basically completely in an offline mode. The land surface model having eight fields. So volumetric soil water layer 1, 2, 3, 4, and the soil temperature layer 1, 2, 3, 4 are basically the target. And this was basically done rollout forecast until 60 days. And this is the anomaly correlation coefficient for soil moisture at layer 1. You can see it's coming down as we are going higher at the lead time, and the RMSE is basically going up. And then we also did another case study for central US drought, which was in 2012. Also a big event and really important for seasonal and sub-seasonal scales. But this is just an offline AI land model. So that's the state we are at on the AI land model. We're further developing it, testing it, validating it. Uh, Parallelly, we are also building the AI ocean model with the same philosophy, with the hill peaks mesh, but taking the GODAS reanalysis data, which is like 5 days, and going up to 300-meter depth. So we are not going for decadal scale simulations, and this was so 300 depth meter also was the one that was taken by the ocean linked atmosphere paper. And then the ocean model will have forcings from the atmosphere and from the land, and then we are taking the 3D temperature and 3D salinity as the like the features of the AI ocean model. And then I wanted to just show, like, we have a library for diffusion based data simulation. Now that will be ingested, like when everything we put together. Uh, there are station observations, there are FluxNet sites. We can actually improve the AI land model based on that. So the data simulate it's not just data simulation. So the diffusion based data simulation can also be used to improve these AI based the weights of the AI based models. So that's the goal for that. So this deep assimilate, it's available on PyPy as a pip install library. That's so that would also be ingested, like everything when it comes together as EarthMind S2S. And then what we are going towards right now is like everything diffusion and its derivatives like flow matching and distillation models, trajectory consistency distillation or latent consistency model. So yeah, with that, I would like to close and thank the organizers for giving me a chance to talk about the like different components that we are building. The EarthMind S2S as the like bigger project, but then the AI land model and the AI ocean model. And the goal is basically also to start an AI atmosphere model which complements the atmosphere and the land and ocean model, so the S2S model can actually run. Yeah.
Thank you very much, Manmeet, for this nice overview of the S2S system. And yeah, I would like to ask people if they have some question to put it in the Q&A part. You already have one. If you'd like to check it.
Okay, so yeah, this question is from uh, Abdu Mudo. I'm sorry if I'm pronouncing your name wrong. Uh, it says, it's really interesting topic for me. I never used such kind of methods. Could you explain me an email? Which kind of programs and steps need to do in our territory? What kind of open sources you have used in this work? Yeah, I can basically send an email. I can explain how. Okay, so it's from Tajikistan. So these are basically, first of all, global models. So and this the AI S2S that I'm talking about is basically point at 0.25 degrees, so 25 kilometers. Uh, it's a global model, so definitely there is the grid boxes for Tajikistan. Now we have to understand one thing, that when we are going to like high resolution, there is a limit that we have in computing and disk space that we have as a global community. So at S2S scales, at long lead time scales, we cannot go for like very high resolution, like 1 kilometer resolution or 500 meter resolution. uh, so those are the compromises that we have done. We need to do. The second question was what kind of open source data or open source softwares I have used. So this everything was basically done in PyTorch, and all these things like Hillpix is from NVIDIA's Earth to Grid. The unit model or the transformer, those are all open source models. So everything is basically open source in this case. Uh, yeah. Okay, so the second question is from Senlin. Yeah, it says quick question for model training. Notice that you aggregated hourly data to daily mean for training. Would this smooth out daily extreme values, which prevents you from capturing extreme events? Have you tried or do you plan to train based on sub daily? Okay, so yeah, Senlin, actually, the short range models, they are all trained on hourly or 6 hourly data sets. For example, GraphCast, ForecastNet, like Pango Weather, or those kind of models. So I was in my presentation, if I can go back to the slide on the hill picks, where they were showing the hill picks work. So you can see that Pangu weather 24 hour and Pangu weather 3 hour. So if you have to go, what this I think at to some extent this has been established, that if you use a model which is having a smaller delta t, it won't have a long lead skill in the pure AI based model version. So you can see a 24-hour model where you aggregate 24 hour and you have time t as input and t plus 1 day as target. Or if you have a 3 hour model where you aggregate with 3 hours, and if you have time t as input and t plus 3 hour as like, or aggregated at every 3 hours, that those models are not stable for long lead times. And that's the reason I think these two models, the GraphCast DeepMind and GraphCast Earth2Map, are like not like these models are not showing stability. uh, I think if someone trains a daily graph model, that also should be stable. So I have to your question, I have actually trained sub daily models, but the goal here is actually to build the S2S, and to go to the S2S scales, we actually need to take a higher delta T. Uh, okay, so then there is another question from Cass. If I understand correctly, each component, ocean, atmosphere, land forecast in the rollout consists of two-step forecast for individual component, merging and correction using the forecast from other components, so that every time each component is forecasted individually and then corrected or updated using the forecast from other. Yes, that's right. Actually, that's the way. So this is the way in which physics-based coupled ocean atmosphere models also work. You inherently they are like built as offline versions, but then you run, for example, atmosphere for certain number of time steps. Ocean has a longer time step delta t, and then at certain time there is a coupling time at which they are coupled, so the data exchange basically happens, which you rightly said, it's like, can think of like as correction. So that happens, and then the models, they run again as offline models. So that happens. uh okay, so the next question is from Z Zhang. uh Thank you for comprehensive presentation. Yeah, thank you. Question regarding the two offline test examples, Mississippi wetland and central US drought. Skills shown with ACC down to 0.5 after around 30 days is exciting. Is it an AI offline land model, and what is the atmospheric forcing from? Is it also an AI atmospheric forcing driving an AI land? Okay, so right now, since this talk actually, I wanted to focus on the AI land model. I already have stuff that is running. I don't have the visualization for that for the AI atmosphere model. Uh, this was a pure offline AI land model. The forcing was ERA5 atmosphere forcing, and I ran until the off like, but the land model was would generate the outputs or the forecast based on like this hill picks, the EarthMind AI land model. So this the yeah the AI atmospheric forcing driving, it's not an AI atmospheric model right now. It is just ERA5 atmospheric forcings, just like you would basically run no MP in an offline mode. Uh, so I will, that's the next thing to do, but yeah, this is an offline model right now. uh, so then the next question is from Cass. When initializing the model, you min-max scale features across the spatial field. I don't recall seeing the approach even often before. What is the motivation for this? Did you observe improved learning? What I have basically understood doing all these things over many, like last 3 or 4 years, is that like even I was, because I come from like a weather and climate background. So when I first saw how the models were trained, they would take a like the min max or mu standard deviation of the entire data set. So that's how you're right. You won't see this this being used in traditional analysis based papers, where you would basically sometimes also take seasonal climate or monthly climatology and then at each grid point. That's not what is done when you are training an AI based model, whether it is a land model, atmosphere model, or ocean model. But we need to do this because think of it in this way. If you normalize over each grid point, the spatial context would be lost. So all the values will come in the range of 0 to, let's say, -1 to 1, or 0 to 1. But in the absolute terms, uh, as you go more towards the North Pole or away from the equator, it will get colder. You come towards the equator, it will get hotter. So that context of the absolute information should also be there in your deep learning model. Otherwise, your model is just seeing the data. So that's the reason we need to take this like this like absolute min max or mu standard deviation. Uh, Okay, so next question is from Liang from Zongliang Yang. Thank you for excellent. Thank you, Liang. Exciting to see the progress in S2S with fully coupled. It would be land, atmosphere, ocean system. It would be good to see systematic tests again. Heat wave, winter freeze, droughts, wildfires. Yeah, and compare their predict. Actually, yeah, that's the ongoing work. Yeah, and thank you so much, Liang. So Liang is the one who is basically uh, he has been the one who is guiding this work all through. We right from the start of this EarthMind S2S. So yeah, we'll get back to you, Liang. Uh, and then from an anonymous attendee, thank you for your explanation. Could you send me your email? Oh yeah, maybe. Yeah, I will just copy this email ID, but and Sohail, if you can maybe share my email with any of the participants if they actually need. Uh, and then the last one that I see is thank you for the presentation. How many parameters does your model have? Was training computationally heavy? How much time did the training take? What hardware did you run on? So this model right now is not that heavy. It is basically it's actually a 3D unit model. Takes about 20 or 25 GB of GPU RAM. I trained it on 80 GB A100s, and this model has been trained on TAC. So, but also one thing to remember is like I have used a pretty coarse version of Hillpix, that is 12 cross 64 cross 64. Uh, Typically, eventually we would like to go to maybe 128 cross 128 or 256 cross 256. In that case, our GPU requirements will go up. So yeah, H100s or A100s, that's the kind of machine that we need to use. Yeah, thank you.
Thank you very much, Manmeet. I have a small question. It's about the anthropogenic impact and effect. Um, how much do you think this AI-driven model would capture the anthropogenic impact, like irrigation or land use change, like deforestation, if they are not already there in the forcing, I mean, in the driving forcing, let's say, like Earth doesn't have irrigation, for instance.
That's a very good question. I think first, like one way, like the most direct way to deal with that would be to have that as a forcing. But then if we don't have it as a forcing, I have seen, like, I think AI too, Allen Institute of AI, I think they have the model which they are saying it can run for like maybe 1,000 year simulations. I think in those cases, the data itself would have that information, and this has to be seen. I don't think that there is already a paper that has answered this question. But my it would be a good hypothesis to test. that whether because the data, the ground truth or the ERA 5 reanalysis that will have the information for volcanic eruptions, for anthropogenic forcings, for like for everything that the different kinds of experiments that we do with the physics-based climate models. My understanding is that these models should learn that information from the data because uh, because the rollout forecast is something which is kind of I don't understand even now how it works because you are just training the model to predict the next time step, and this is I think this is the beauty of even the state of the art LLMs. Like they are next word prediction models, but they can do summarization and translation and all the different tasks for which they were not trained on. So my guess is like the data is it we are maybe at a stage where the data is driving, the models are becoming so good. Uh, in the absence of an external forcing, if we don't have the forcing data, uh, this is a good hypothesis to test. But the first approach would be to try and, for example, in the climate models, we would have the yearly CO2 emissions value in parts per million, right? That it goes as forcing to these climate. I mean, the models which do not have like carbon or a model which actually can simulate the carbon dioxide emission sets as well. So that goes as forcings in these models also. Even in the future projections, SSP 245, 126, 585, we have different models which actually provide forcings to these climate models. I think if we do in such a way, these AI-based Earth system models would be able to respond to those forcings. But if we don't give that explicitly, then we have to expect the data to basically guide us. Yeah.
Thank you very much. I see that you have one last question, I think.
Yeah. Uh, okay, so the question is, yeah, that question is, oh yeah, in the open. I found SwinRDM model very interesting as I am now working on climate downscaling. Wanted to ask where does SwinRDM stand accuracy wise compared to current latest and most accurate downscaling models. So SwinRDM uses diffusion, and diffusion it has been shown across the board is the mathematical operator that we go with for downscaling. It was 5 years ago, it was, or 7 years ago, it was CNNs, SRCNN, maybe 10 years ago. Then we had GANs, generative adversarial networks. 3 years ago, we had transformers. Now we have diffusion, distillation, flow matching. Swin RDM is one example of diffusion, but you can use all sorts of diffusion models these days. Uh, so yeah, it is. It stands like it's the state of the art. The diffusion models. Swin RDM, I think, uses a particular type of maybe DDPM or the other diffusion. Also, does it have any limitations such as it only performs well on certain type of climate variables and performs worse on others? Uh, I would say uh, again, like these things, yeah, there is no standard answer to these questions. There are a lot of works, a lot of AI weather papers, but a lot of these questions actually need to be answered. Yeah,
Okay, thank you very much. Great talk. Yeah,
yeah.
if you have one more question.
One more question is there. Yeah. How can we reach the data from Meteor or any other data? Uh, as I think this question basically means how can we maybe train or transform meteorological data to a machine learning model. So you basically just read the data in X-ray or the ZAR data and put it on the GPU, just like the computer vision image data is trained. Just treat it as numbers. Any open source links you would recommend for water flow, temperature, precipitation, soil moisture, and other parameters with normal accuracy and other knowledge. Uh, I think the Copernicus CDS is a really good source which has a lot of data sets, including ERA 5 reanalysis, ERA 5 land. You would get data for water flow, temperature, precipitation, soil moisture, all other variables. Now, whether you want high resolution, whether you want now that's a different. I'm actually open to if anyone is interested in more details, we can chat over email. But I think that's what I understand with this question. Yeah, thank you.
Thank you very much, Manmeet. And just one small comment about the scorecard that you showed. It's an evolving scorecard, so it has changed since 2023.
Okay.
So I mean, all the model are evolving quite fast. So
You mean the weather bench or the AIFS
yeah,
weather bench?
exactly.
Okay. Yeah. Okay.
And I would like to thank you very much for your very nice talk, and also to remind all the attendees to check this Panglass conference for next July. I've put the link in the chat again for those who were not there at the beginning. Thank you very much, and see you in the next webinar. Thank
Thank
you.
you.
Bye.
Thank you so much, Sohail and Shannon. Yeah, thank you. Yeah.
Thank you.